The cosmos whispers its deepest secrets through patterns etched across the night sky. This video, Inside the Minds of the Universe, what the most puzzling cosmic patterns reveal about creation, deciphers that hidden language. By the end, you will see the universe not as a chaotic void, but as a structured, almost intelligent design. We will explore why galaxies unfurl in perfect spirals and what the faint afterglow of the Big Bang tells us about the beginning of everything. Could the strange alignment of objects billions of light years apart rewrite our laws of physics? This journey reveals that these cosmic blueprints are clues to the very nature of existence itself. What does it mean to live in a universe that seems to follow a grand mathematical plan? These cosmic threads weave a story that begins with the faintest whisper from the dawn of time. The universe is not a random scattering of stars but a grand design, a blueprint written in the language of physics. This underlying order is a signature of creation itself, a fingerprint left behind by the forces that birthed everything we see. From the spooky connections between quantum particles to the vast, web-like filaments of galaxies stretching across billions of light years, patterns are the universe's fundamental nature. This cosmic architecture emerged from the primordial soup of the Big Bang. In that first unimaginable moment, a period of hyper-accelerated expansion called inflation stretched tiny quantum fluctuations into the seeds of all future structure. Think of it like blowing up a balloon with microscopic writing on it. As the balloon inflates, those tiny scribbles are stretched into vast, continent-spanning letters. In the same way, the minuscule ripples in the newborn universe were magnified into the gravitational wells that would eventually pull in dark matter and gas, forming the skeleton of the cosmic web. Dark matter, that mysterious invisible substance that outweighs normal matter 5 to 1, acts as the framework. Its gravitational pull guides ordinary matter into the vast walls and threads we observe, with glittering galaxies tracing the outlines like dew on a spider's web. Projects like the Sloan Digital Sky Survey have mapped the positions of millions of galaxies, revealing a distribution that is eerily structured. This cosmic map looks surprisingly similar to another complex network, the neural connections of a human brain. Is this resemblance a mere coincidence, or could it be a hint of something deeper? Does it point toward a universal consciousness, or is it simply the beautiful and inevitable outcome of blind physical processes playing out on the grandest possible stage? To answer that, we must learn to read the universe's mathematical handwriting, a code embedded in the very fabric of reality. That same mathematical handwriting is visible right here on Earth in the spirals of a Nautilus shell. Each new chamber grows in perfect proportion to the last, following a precise, elegant curve. This is the fingerprint of the Fibonacci sequence, a series of numbers where each one is the sum of the two before it. 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, and so on, creating the sequence 0, 1, 1, 2, 3, 5, 8, 13 into infinity. When you plot these numbers geometrically, they produce a spiral, one that appears again and again throughout the natural world. You see it in the arrangement of petals on a rose, the curve of a fern, and the unfurling face of a sunflower, where the seeds pack themselves in spirals based on Fibonacci numbers to maximize space and sunlight. This is not just a pretty pattern, it is a blueprint for efficiency, a way for living things to grow using the least amount of energy. But this blueprint is not confined to our planet. Look up at a spiral galaxy like our own Milky Way, and you will see that same fundamental shape. The arms of the galaxy swirl outwards in a logarithmic spiral, a pattern mathematically linked to the golden ratio, a special number approximately equal to 1.618. This ratio appears when a line is divided so that the whole length compared to the longer segment is the same as the longer segment compared to the shorter one. It is a proportion that the human eye finds inherently pleasing, and it governs the formation of hurricanes, the rotations of distant galaxies, and even the rhythmic timing of planetary orbits. Why would a number derived from simple division on Earth appear in the architecture of the cosmos? Mathematicians like Mario Livio suggest these patterns are not coincidences. They are the inevitable outcome of fundamental physical laws, the most efficient solutions to the problems of growth and structure. Does this prevalence of mathematical constants point to a universal language, a single set of rules that governs everything from the smallest seed to the largest galaxy? This harmony suggests a cosmos built on a foundation of numbers, a symphony playing out on every scale. To understand this symphony, we must listen for the faintest echoes of its first note. That symphony of numbers finds its origin in a faint, cold whisper that fills all of space. To hear it, we must journey back to a time when the universe was just 380,000 years old. Before that moment, the cosmos was a searing, opaque fog of plasma and light, too dense for photons to travel freely. Then, in an event cosmologists call recombination, the expanding universe cooled enough for atoms to form, allowing light to break free and travel across the cosmos for the very first time. That primordial flash of light is still with us today, stretched by the expansion of the universe into a faint microwave glow that bathes the entire sky. This is the cosmic microwave background, and it is our most profound window into the universe's infancy. It is a fossilized snapshot, a baby picture of creation. When scientists like George Smoot first mapped this background radiation with satellites like COBE, they expected to see a perfectly smooth curtain of energy. Instead, they found it was subtly mottled with tiny temperature fluctuations, areas that were just millionths of a degree warmer or colder than their surroundings. These anisotropies are not random noise. They are the imprints of the universe's first structures, the gravitational seeds from which everything we see would eventually grow. Those slightly warmer spots were regions of space that were ever so slightly denser, their extra gravity beginning to pull in dark matter and gas. Over billions of years, these tiny ripples were amplified into the vast cosmic web of galaxies and clusters we observe today. Satellites like Planck have measured these patterns with incredible precision, creating a map of the infant universe that confirms our theories of cosmic inflation. The statistical distribution of the hot and cold spots matches the prediction that they were born from quantum fluctuations, microscopic wrinkles in spacetime that were stretched to cosmic proportions in the universe's first fraction of a second. Yet, this map holds profound mysteries. One of the most puzzling is the so-called axis of evil, a strange, large-scale alignment in the temperature patterns that seems to defy the cosmological principle, the idea that the universe should look the same in all directions. This unexpected alignment challenges our standard models and sparks intense debate. Are we seeing a statistical fluke, a ghost in the machine? Or does this axis point toward a deeper, more fundamental asymmetry in the laws of physics, a preferred direction written into the fabric of reality at the moment of creation? What do these primordial ripples tell us about the universe's initial conditions and its ultimate fate? They are a direct link to creation's first moments, a blueprint that guided the construction of everything that followed. This fossilized light does not just show us where we came from. but it also reveals the invisible forces that continue to shape our cosmic destiny. This fossilized light reveals a universe that is far from a random scatter of stars. It shows the faint outline of a colossal architecture, a cosmic web that connects all of matter. Picture the universe not as a simple expanse, but as a sponge, with dense, glowing filaments of galaxies woven together and separated by unimaginably vast, dark, and nearly empty voids. This is the largest structure we know, a web spanning billions of light years. Its construction began with dark matter, that invisible scaffolding whose gravity started to pull the first strands together. Over billions of years, gravity acted like a master sculptor, amplifying the tiny ripples from the cosmic microwave background into this magnificent and intricate network. Supercomputer simulations, like the famous Millennium Run, have recreated this entire process. They show how dark matter collapses into a filigree of threads, with ordinary matter, the gas that forms stars and galaxies, simply flowing along these invisible rivers of gravity. The result is a map of the cosmos that looks eerily familiar. It resembles the neural network of a brain, the intricate pattern of veins in a leaf, or even the vast digital connections of the Internet. Is this resemblance a profound clue, a sign of some universal principle of connectivity that operates from the microscopic to the cosmic scale? Or is it simply the beautiful, inevitable outcome of gravity working on an unimaginably large canvas? To trace the web's growth, scientists use a cosmic ruler known as baryonic acoustic oscillations. This complex term describes a simple echo from the early universe. In that first hot, dense state, ordinary matter and light were locked in a tight struggle, creating spherical pressure waves that rippled outward through the plasma, like sound waves moving through air. When the universe cooled and atoms formed, these waves froze in place, imprinting a preferred scale on the distribution of matter. We can still see this imprint today as a subtle tendency for galaxies to be separated by a specific distance, about 500 million light-years. By measuring this standard distance in galaxy surveys, astronomers can map the expansion history of the universe and chart the three-dimensional structure of the cosmic web. This mapping has revealed our own cosmic address within a supercluster we call Laniakea, a Hawaiian word meaning immense heaven. Laniakea is a gravitational watershed, a vast collection of over 100,000 galaxies, including our own Milky Way, all flowing together toward a common gravitational center. Beyond our local supercluster lie even more immense structures, like the Sloan Great Wall, a colossal filament of galaxies so vast it challenges our understanding of how such a thing could form so quickly after the Big Bang. Yet for all this dense structure, the web is defined just as much by its emptiness. The Boötes void is one of the largest known voids in the universe, a spherical region of space so empty that if our Milky Way were at its center, we would not have known other galaxies existed until the 1960s. In a volume of space hundreds of millions of light-years across, there are only a handful of galaxies where there should be thousands. This profound emptiness forces us to ask if our models of galaxy formation are complete, or if some regions of the cosmos were simply left behind in the rush of creation. This intricate balance between the densely woven filaments and the cavernous voids reveals a universe of organized complexity. Is this cosmic web the ultimate expression of gravity's patient work, or does its interconnected nature point to something more fundamental, a universal principle that everything is linked? The answer may lie not in the vastness of space, but in the bizarre behavior of the smallest particles in existence. That unseen sculptor leaves its signature everywhere. We watch galaxies spin, their outer stars whipping around at speeds that should send them flying off into the void. According to the laws of gravity, the visible matter in a galaxy, all the stars and glowing gas, simply does not provide enough gravitational glue to hold these speeding stars in their orbits. The only explanation is that each galaxy is embedded within a massive, invisible halo of something that exerts a powerful gravitational pull, something we cannot see. This was the revolutionary work of astronomer Vera Rubin in the 1970s. By meticulously measuring the rotation curves of galaxies, she found that stars far from the galactic center moved just as fast as those near the center, a clear violation of what Newtonian physics predicted if only visible matter was present. Her findings provided some of the strongest evidence for dark matter, an invisible substance that comprises about 27% of the universe. This mysterious material does not emit, absorb, or reflect any light, making it completely transparent. We only know it is there by the gravitational hand it places on everything we can see. It acts as the cosmic framework, the skeleton upon which the glittering flesh of galaxies is draped. Its nature, however, remains one of physics' greatest puzzles. Theorists categorize possible dark matter particles by how fast they moved in the early universe. Cold dark matter moves slowly, and its models perfectly predict the large-scale structure of the cosmic web we observe. Warm dark matter is a middle ground, while hot dark matter moves near the speed of light and is largely ruled out because it would have prevented small galaxies from forming. The most compelling evidence for this invisible scaffolding comes from cosmic collisions like the Bullet Cluster. This is a system of two galaxy clusters that have smashed right through each other. When astronomers mapped it, they found something astonishing. The pink glow of hot, normal gas detected by X-ray telescopes was slowed and separated from the bulk of the mass, which was mapped using gravitational lensing, the way the cluster's gravity bends light from background galaxies. The mass, the true source of gravity, was not where the visible gas was. It had passed through the collision unscathed, just as dark matter should, proving it is a real, physical substance that interacts predominantly through gravity. To hunt for these elusive particles, scientists are trying everything. Deep underground, in mines shielded from cosmic rays, experiments wait for the faint bump of a dark matter particle hitting an atomic nucleus. In space, telescopes like the Fermi Gamma Ray Space Telescope scan the skies for indirect signals, like gamma rays produced if dark matter particles annihilate each other. And at the Large Hadron Collider, physicists are smashing protons together at unprecedented energies, hoping to create dark matter in the lab. So far, it has evaded every direct search. Could dark matter be a gateway to understanding hidden dimensions or new physics beyond our current standard model? Its enigmatic role in patterning the cosmos is undeniable, a hidden hand that guided the formation of everything we see. Yet for all its power, dark matter's gravitational pull is only part of the story. Another, even more mysterious force is now taking control of the universe's destiny. While dark matter pulls the cosmos together, a far more mysterious force is now tearing it apart. We have long known the universe is expanding, but the stunning discovery at the turn of the millennium was that this expansion is not slowing down. It is accelerating, speeding up with every passing moment. This cosmic acceleration is driven by a repulsive force we call dark energy, a component that makes up a staggering 68% of the entire cosmos. Its discovery came from observing a specific kind of stellar explosion in incredibly distant galaxies. Two independent teams, one led by Saul Perlmutter, were using these supernovae as cosmic mile markers. They expected to see the light from these ancient explosions stretched and dimmed by a certain amount, indicating a universe whose expansion was gradually slowing under gravity's pull. Instead, the light was far fainter than it should have been. The only explanation was that these supernovae were much farther away than anyone had calculated, meaning the space between us and them had stretched at an ever-increasing rate over billions of years. The universe was not just expanding, it was flying apart faster and faster. This revelation earned the teams the Nobel Prize and completely upended our understanding of cosmic fate. So what is this dark energy pushing everything apart? The leading candidate is the cosmological constant, an idea Einstein himself once proposed and then discarded. It suggests that empty space is not truly empty but possesses its own intrinsic repulsive energy. Think of it as the cost of having space itself. As the universe expands, more space is created, and with it, more of this repulsive energy, leading to a runaway acceleration that grows stronger over time. Another, more dynamic possibility is a field called quintessence, a fluid-like energy that could change over time and vary across space. Whether it is a constant or a changing field, dark energy's effect is to act as a form of anti-gravity, but only on the very largest scales. Within a galaxy, gravity easily dominates, holding stars together. But across the vast emptiness between galactic clusters, where matter is sparse, dark energy's repulsive push wins the battle. This fundamental conflict shapes the ultimate destiny of everything. If dark energy is a constant force, as the cosmological constant suggests, the universe faces a slow, cold death known as the Big Freeze or heat death. Galaxies will be pushed ever farther apart, stars will burn out, and the cosmos will expand into an eternal, dark, and near absolute zero wasteland. But if dark energy intensifies over time, a more violent end awaits: the Big Rip. In this scenario, the repulsive force would eventually become so strong that it would overcome all other forces. First, it would tear apart galactic clusters, then individual galaxies. In the final moments, it would rip apart stars, planets, and even atoms themselves, shredding the very fabric of spacetime. To understand which path we are on, scientists use tools like Baryon acoustic oscillations, the frozen sound waves from the early universe, as a standard ruler. By measuring how this preferred distance between galaxies has changed over cosmic time, we can chart the expansion history with incredible precision and probe the nature of dark energy itself. This leads to a profound and unsettling question. Is dark energy a fundamental property of the vacuum of space, a cosmological constant woven into the universe's foundation? Or does its existence force us to reconsider our most cherished theory, Einstein's general relativity? Perhaps gravity itself behaves differently on the largest scales than we thought. This accelerating force does more than just dictate our future. It reshapes our entire view of cosmic evolution and steers us back toward the very beginning, to the quantum origins of the patterns we see. The vacuum of space is not a still and silent emptiness. It is a vibrant, churning sea of potential, where particles and energy flicker into and out of existence in a relentless, probabilistic dance. This is the realm of quantum fluctuations, the ultimate source of all the structure we see in the cosmos. The grand tapestry of galaxies, the vast cosmic web, every star and planet, all trace their origin back to these subatomic tremors in the fabric of spacetime. According to the Heisenberg uncertainty principle, it is impossible to have a perfectly empty, zero-energy state. Even in a perfect vacuum, there is always a tiny, irreducible uncertainty in energy, a fundamental jitter that allows for the spontaneous creation of virtual particle pairs, matter and antimatter, which annihilate each other almost instantly. In the first fleeting fraction of a second after the Big Bang, the universe underwent a period of hyper-accelerated expansion called inflation. During this incredible growth spurt, the universe doubled in size over and over again, perhaps 100 times in a row. This process of inflation acted like a cosmic magnifying glass, stretching those infinitesimal quantum fluctuations from the subatomic scale to proportions larger than the observable universe. The microscopic wrinkles in the newborn cosmos were blown up into macroscopic ripples in the density of matter and energy. These ripples became the gravitational seeds, the slight over densities that would, over billions of years, pull in dark matter and gas, eventually collapsing into the first stars and the glittering galaxies we observe today. This profound connection means that the largest structures we can see were born from the smallest events we can describe. The work of physicists like Stephen Hawking helped cement this theory, showing how these quantum jitters would inevitably leave a permanent imprint on the cosmos. That imprint is the pattern of hot and cold spots we see in the cosmic microwave background, the fossilized light from the universe's infancy. The statistical nature of these patterns is a crucial clue. Most inflationary models predict that these primordial fluctuations should be Gaussian, meaning their distribution follows a specific, bell curve-like randomness. If, however, future observations with satellites like Planck were to find strong evidence for non-Gaussian statistics, it would be a revolutionary discovery. It would mean the fluctuations were not purely random, hinting at more complex physics during inflation, perhaps even touching on the elusive theory of quantum gravity. This quantum foundation forces us to confront a staggering possibility. If our entire universe is the result of one specific set of amplified quantum fluctuations, what about all the other possibilities? The inflationary model naturally suggests a multiverse, a vast and perhaps infinite ensemble of universes, each with its own unique set of physical constants and cosmic patterns, each a different roll of the quantum dice. Our universe, with its specific laws that allow for our existence, would be just one bubble in an infinite cosmic foam. This revelation forges a deep and unbreakable link between the quantum world and the cosmic scale. The same principles that govern the behavior of a single electron seem to dictate the architecture of the cosmos. This prompts a fundamental question about the nature of reality itself. Is this profound symmetry, this repetition of pattern from the infinitesimal to the immense, simply a happy accident, or is it the signature of a deeper, more unified law waiting to be discovered? The same mathematical perfection found in a snowflake reveals a deeper truth about the cosmos. A falling snowflake is a masterpiece of symmetry, its 6 arms branching in perfect harmony, a pattern dictated by the fundamental laws of water molecules crystallizing in the atmosphere. The early universe was a place of even more profound symmetries, a hot, dense soup where the forces of nature were unified and all particles were massless, racing through a perfectly uniform sea of energy. But just as a snowflake's perfect symmetry is broken when it lands and melts into a unique, asymmetrical puddle, the universe had to break its perfect symmetries to create the rich, complex world we inhabit today. This process is known as spontaneous symmetry breaking. Picture a pencil balanced perfectly on its tip. In that moment, it is symmetrical, identical in every horizontal direction. But the slightest disturbance, a random quantum fluctuation, will cause it to fall, choosing one specific direction and breaking that perfect symmetry. The universe underwent a similar series of falls as it expanded and cooled. One of the most crucial breaks involved the Higgs field. As the cosmos cooled, this invisible energy field, which had been in a symmetrical, high-energy state, shifted into a lower energy state that filled all of space. This event, akin to a universal phase change, is what gave mass to fundamental particles through the Higgs mechanism. Particles that interact strongly with this field, like the top quark, became heavy, while others, like the photon, remained massless. Without this broken symmetry, there would be no atoms, no stars, and no us. an even more pivotal break may explain one of the universe's greatest mysteries, why we are made of matter at all. According to our best theories, the Big Bang should have created equal amounts of matter and antimatter, which would have promptly annihilated each other, leaving behind a sea of pure light. The fact that we exist means something tipped the scales. The answer appears to lie in a subtle cosmic bias called CP violation. This is a violation of the combined symmetries of charge and parity. In simple terms, it means that the laws of physics treat particles and their mirror image antiparticles slightly differently. This tiny asymmetry, discovered in the behavior of certain subatomic particles, meant that for every billion annihilations in the early universe, one matter particle was left over. That 1 in a billion remnant is everything we see. This preference for matter over antimatter is eerily mirrored here on Earth in the very building blocks of life. Nearly all amino acids, the components of proteins, are left-handed, a specific chiral orientation. While the reason is not fully known, some scientists theorize this biological asymmetry could have a cosmic origin, seeded by the same fundamental biases that gave us a matter-dominated universe. This principle of broken symmetry even shapes the largest structures. Spiral galaxies can spin clockwise or counterclockwise, but there is no overarching reason for a preferred direction. Yet, when astronomers survey the sky, they sometimes find large-scale alignments, vast patches of space where galaxies seem to prefer one spin direction over the other, a possible echo of those primordial quantum fluctuations amplified to a galactic scale. So does this pervasive broken symmetry reflect a deeper, hidden balance in the universe, or is it merely the random outcome of a cosmic coin toss? The quest to understand these alignments leads us to one of the most perplexing patterns in the entire sky, a mystery that seems to point a finger directly at our place in the cosmos. This strange preference for a direction in the cosmos is no longer just a theoretical curiosity. It has a name, and scientists call it the axis of evil. This ominous title refers to a bizarre and persistent alignment found in the cosmic microwave background, the universe's baby picture. The hot and cold spots in this ancient light appear to be subtly correlated along a particular line, a preferred axis that stretches across the sky. This discovery directly challenges the cosmological principle, the foundational idea that the universe is isotropic, meaning it should look the same in every direction with no special place or orientation. If the universe is truly a uniform cosmic soup, why would its oldest light whisper of a specific alignment? The statistical significance of this axis, first spotted in data from the WMAP satellite and later confirmed, albeit with more nuance by the Planck mission, is too strong to be easily dismissed as a simple fluke. The odds of it being a random statistical artifact are incredibly low, forcing cosmologists to confront an uncomfortable possibility. Could our universe have a built-in preferred direction, a fundamental lopsidedness written into its DNA? The mystery deepens when we look at other cosmic structures. Astronomers, including researchers like Kate Land, have observed another stunning alignment. The rotation axes of supermassive black holes at the centers of quasars, objects separated by billions of light years, appear to be correlated. It is as if these monstrous engines, scattered across the vast emptiness of space, are all spinning in concert, like a cosmic ballet choreographed on an impossible scale. How can objects so unimaginably far apart, far beyond each other's gravitational or electromagnetic influence, possibly share a coordinated orientation? The sheer scale of these alignments defies our conventional understanding of cause and effect. So what could possibly explain such a coordinated cosmic display? One possibility is that we are being fooled by our own data. that subtle systematic errors in our telescopes or in how we filter out foreground light from our own galaxy are creating an illusion of structure. But after years of intense scrutiny, this explanation is becoming harder to defend. If it is not an error, then we must venture into the realm of new physics. Could these alignments be the fossilized imprint of cosmic strings, hypothetical, infinitely long defects in spacetime left over from the early universe, whose immense gravitational fields could have sheared space into a preferred alignment? Or perhaps they are scars from immense primordial magnetic fields that once permeated the cosmos, guiding the formation of structure along a specific direction. Some theorists even suggest these patterns are a hint of something that happened before the Big Bang, a pre-existing architecture that imprinted itself onto our newborn universe. Others see it as a shadow of the multiverse, a gravitational tug from a neighboring universe in the infinite cosmic foam, subtly influencing our own. Are these vast alignments merely incredible statistical flukes, cosmic mirages in the data? Or do they point to a deeper layer of cosmic architecture, a fundamental anisotropy we have yet to comprehend? These enigmas push at the very boundaries of our knowledge, forcing us to ask if the universe itself is running on a kind of computation, a set of instructions more complex and interconnected than we ever dreamed. The vast cosmic alignments seem to follow a hidden logic, a set of instructions written into the fabric of reality. This logic finds its most radical expression in a theory that reimagines the universe itself as a cosmic computer. The holographic principle, championed by physicists like Leonard Susskind, proposes a staggering idea. Everything we perceive in our three-dimensional world, every galaxy, star, and person, might be a complex projection of information encoded on a distant, two-dimensional surface. Our reality, in this view, is a hologram of breathtaking complexity. This concept was born from the paradoxical physics of black holes. In the 1970s, Jacob Bekenstein and Stephen Hawking discovered that a black hole's entropy, a measure of its information content, is not proportional to its volume as one would expect. Instead, it is precisely proportional to the surface area of its event horizon. This was a profound clue. It suggested that all the information about everything that falls into a black hole is not lost within its vast interior, but is somehow painted onto its two-dimensional boundary. The holographic principle takes this black hole thermodynamics and applies it to the entire cosmos. It suggests that the universe itself stores its information on its outer boundary, and what we experience as reality is a projection from that cosmic hard drive. This leads to a specific mathematical framework known as the AD/S/CFT correspondence. It demonstrates a perfect duality between a gravitational theory in a hypothetical anti-de Sitter space and a conformal field theory, a quantum theory without gravity, operating on its lower dimensional boundary. In simpler terms, it shows that a universe with gravity can be completely described by a quantum theory on its surface, with no loss of information. This is the mathematical bedrock of the holographic idea. From this springs the even broader concept of digital physics, the notion that the universe is fundamentally discrete, not a smooth continuum. At the tiniest possible scale, the Planck scale, reality may be composed of indivisible bits of spacetime, like the pixels on a screen. The cosmos would then be a vast quantum computer, processing these bits according to a set of underlying algorithms, calculating its own evolution moment by moment. Scientists are actively searching for evidence of this pixelation. They scrutinize the cosmic microwave background, the universe's oldest light, looking for telltale signs of a fundamental graininess in the fabric of spacetime, a subtle blurring that would betray its digital nature. This computational view inevitably leads to a provocative question, one debated by philosophers like Nick Bostrom. If the universe operates on computational principles, could it actually be a simulation? The argument suggests that an advanced civilization could, in theory, create a simulation so complex it contains conscious beings. If such simulations are possible, then the number of simulated realities would vastly outnumber the one base reality. Statistically, we are more likely to be in a simulation than not. This is not a claim that we are in a simulation, but a fascinating logical puzzle about the nature of existence. If the universe computes its own evolution, what does that imply for our own consciousness? Are our thoughts and experiences merely the output of an unimaginably complex calculation running on a cosmic processor? This perspective forges a deep and unexpected link between the nature of reality and the search for other minds in the cosmos. If the universe is indeed a form of computer, then the search for extraterrestrial intelligence becomes a quest to find other, perhaps more advanced, programmers or processes within the same vast system. Scanning the heavens for a message is the ultimate test of our cosmic loneliness. For decades, scientists with the search for extraterrestrial intelligence, or SETI, have trained radio telescopes on the stars, listening for a pattern that stands out from the natural hum of the cosmos. This is not a search for any pattern, but for one that bears the unmistakable signature of design. It is the hunt for a signal that is engineered. When a powerful, narrow-band radio burst known as the WOW signal was detected in 1977, it matched the profile of a potential artificial transmission. It came from a specific point in space, lasted for 72 seconds, and was never heard again. Decades later, we have fast radio bursts, or FRB, incredibly energetic pulses that last mere milliseconds. While most appear to be one-off events, one source, designated FRB 1211-2, has been caught repeating. This repeating pattern, with its complex structure, immediately sparked speculation. Could it be a natural astrophysical object, like a magnetar, a highly magnetized neutron star? Or, in the absence of a definitive natural explanation, could it be the exhaust plume of an alien starship or a powerful beacon? Experts like Jill Tarter have long argued that the key to this search is statistics. We must learn to distinguish the cosmic background of natural events from a signal that is statistically improbable, one that carries information or a structure that nature, left to its own devices, would be unlikely to produce. This is why many proposed templates for an alien message rely on mathematics, the universe's common language. A sequence of prime numbers, for example, is a compelling candidate. Primes are numbers divisible only by themselves and one, like 2, 3, 5, 7, and 11. They are mathematical facts independent of human culture or biology. A beam of radio waves pulsed in a sequence of prime numbers would be a cosmic shout. It would say, "We understand logic, we understand mathematics, and we are here." To quantify this cosmic quest, Frank Drake formulated his famous equation. It is not a formula to be solved, but a framework for discussion, multiplying together factors like the rate of star formation, the fraction of stars with planets, the number of habitable worlds per system, the fraction where life emerges, the fraction where life becomes intelligent, and crucially, the length of time such a civilization releases detectable signals into space. The result is n, the estimated number of communicative civilizations in our galaxy. The value of n could be 1, meaning we are utterly alone, or it could be in the thousands. We simply do not know. This profound uncertainty fuels projects like Breakthrough Listen, a monumental effort to survey 1 million nearby stars and the centers of 100 galaxies across a wide range of radio and optical frequencies. It is the most comprehensive search for technological signatures ever undertaken, sifting through an ocean of data for that one precious needle of artificiality. So if we one day found such a pattern, an intelligently crafted signal from the depths of space, how would it reshape our understanding of creation? It would force a monumental shift in our cosmic perspective. We would have to confront the Anthropic Principle in a new light. This principle suggests that the universe's physical constants are finely tuned to allow for the existence of observers like us. Finding another intelligence would mean this fine-tuning did not produce just one fragile experiment in consciousness, but at least two. It would suggest that the universe is not just bio-friendly, but abundantly so, teeming with minds. The discovery would be the ultimate symmetry breaker, telling us that our own intelligence is not a singular accident, but part of a broader cosmic pattern of mindful existence. That signal would force us to confront a staggering possibility, one that has been hiding in plain sight within the laws of physics themselves. The universe appears to be fine-tuned for our existence. This is the Anthropic Principle, a concept formalized by physicist Brandon Carter. It suggests that the fundamental constants of nature are not arbitrary, but seem perfectly calibrated to allow for the emergence of life and consciousness. Alter any one of these numbers by even a hair's breadth, and the cosmos as we know it would vanish. If the force of gravity were slightly stronger, the universe would have collapsed back on itself in a fiery crunch shortly after the Big Bang. If it were slightly weaker, matter would never have clumped together to form the first stars and galaxies. Our universe would be a cold, dark, and eternal void of dispersed hydrogen gas. The cosmological constant, which governs the strength of dark energy, is perhaps the most startling example. Its observed value is so incredibly small that it represents one of the worst predictions in the history of theoretical physics. If it were just a little bit larger, the repulsive force would have torn the infant universe apart before any structure could form. We exist in a razor-thin window where this constant is weak enough to allow for galaxy formation, but strong enough to now dominate the expansion, a cosmic coincidence that begs for an explanation. This fine-tuning extends to the very elements that make up our bodies. The creation of carbon, the essential backbone of life, relies on a stunningly precise nuclear resonance. Inside stars, 3 helium nuclei must fuse together to form a carbon nucleus. For this to happen efficiently, the energy levels of the carbon nucleus and the incoming helium combination had to be perfectly matched. Physicist Fred Hoyle famously predicted this resonance must exist, and experiments later confirmed he was right. Without this exact match, the universe would contain very little carbon, and life as we know it would be impossible. This delicate balance forces us to ask a profound question. Why does the universe seem so hospitable to us? Carter proposed 2 main interpretations. The weak Anthropic Principle simply states that we must observe a universe capable of supporting us because we are here to observe it. It is a selection effect. We could not find ourselves in a universe without carbon or galaxies because such a place could not host observers. The strong Anthropic Principle takes a much bolder step. It suggests that the universe must have properties that allow life to develop at some stage in its history. This version implies a deeper necessity, a law or a process that makes a life-friendly cosmos inevitable. So which is it? Are we the beneficiaries of an incredible cosmic lottery, or is there a deeper logic at work? One compelling answer lies in the idea of a multiverse. If inflation is true, and it generates a vast, perhaps infinite, ensemble of universes, each with its own random set of physical constants, then it is no surprise we find ourselves in one of the rare, fine-tuned bubbles where life can exist. In this view, there is no designer, only an immense statistical probability that guarantees a handful of habitable universes in an endless sea of sterile ones. The alternative, of course, is that the fine-tuning is evidence of intentional design, a universe crafted with a purpose. This debate sits at the boundary of science and philosophy, pushing us to question the very origin of these physical laws. Does this delicate balance point toward a creator, or are we simply the conscious inhabitants of one lucky roll of the dice in a cosmic casino with an infinite number of tables? The answer may lie not in the constants themselves, but in the very origin of time, a moment when all the rules were written. The universe runs on a one-way street. This irreversible flow from past to future, the arrow of time, is not just a feature of our daily lives but a fundamental property of the cosmos, etched into the laws of physics by the second law of thermodynamics. This law states that entropy, a measure of disorder or randomness, always increases in an isolated system over time. Think of a sandcastle on a beach. Left alone, the wind and waves will inevitably scatter its carefully sculpted towers back into a formless pile of sand. That is entropy increasing, moving from a state of precise, low entropy order to a high entropy state of disorder. The entire history of our universe is this process playing out on the grandest possible scale. Our cosmic story began with an incredibly improbable event, a Big Bang that was a state of remarkably low entropy. Physicist Sean Carroll refers to this as the past hypothesis, the puzzle of why the early universe was in such a special, organized condition. From that finely tuned starting point, the universe has been sliding down a thermodynamic hill ever since, with entropy steadily increasing as stars burn, galaxies collide, and energy disperses. This inexorable rise in disorder gives time its direction. We remember the past, a state of lower entropy, and move toward a future of higher entropy. There is no physical law that says you cannot see a shattered glass reassemble itself, but you never will, because the odds of countless scattered molecules spontaneously arranging themselves back into a glass are astronomically low. This progression is intimately tied to the expansion of the universe itself. As space stretches, it creates more room for particles and energy to spread out, increasing the number of possible disordered states and driving the entropy ever higher. Black holes are the ultimate entropy engines. These gravitational monsters possess an immense amount of disorder, quantified by the surface area of their event horizons. When matter and energy fall into a black hole, the total entropy of the universe skyrockets. The event horizon acts as a one-way membrane, a point of no return that perfectly embodies the irreversible flow of time. Even our own consciousness is tied to this thermodynamic arrow, the psychological arrow of time. Our perception of a flowing present is likely a direct consequence of our brains processing information in an entropy-increasing universe. We form memories because the past is a state of lower entropy, and our thoughts march forward because that is the direction in which disorder grows. So what set this entire irreversible chain in motion? The answer may lie in cosmic inflation, that brief, hyper-accelerated expansion in the universe's first fraction of a second may have meticulously wound up the cosmic clock, establishing the pristine, low-entropy initial condition that has been unwinding for the last 13.8 billion years. This leads to a profound reflection. Is the arrow of time merely an emergent property, a large-scale consequence of countless particles interacting, or does its relentless one-way flow point to a deeper, fundamental asymmetry in the laws of physics, a broken symmetry in time itself? If time's arrow is not absolute, could the universe eventually reverse its course or even begin the cycle all over again? Perhaps time's arrow is not the final word on cosmic destiny. A phoenix universe dying in a fiery Big Crunch only to be reborn in a fresh Big Bang offers a radically different vision of eternity. This is the cyclic universe model, where creation is not a single, unique event but an endless, breathing rhythm of expansion and contraction. In this view, our entire cosmos is merely one chapter in an infinite story, with no true beginning and no final end. The appeal is profound as it sidesteps the perplexing question of what, if anything, came before the initial singularity. One compelling version is the ekpyrotic scenario born from string theory. It envisions our three-dimensional universe as a membrane or brain floating in a higher dimensional space. A cyclic universe could begin when another parallel brain collides with ours, an impact that delivers an immense burst of energy we would experience as our own Big Bang. The universe then expands, evolves, and eventually contracts, setting the stage for another collision and another rebirth. This model elegantly explains the universe's large-scale smoothness as the brains stretch and flatten before each collision. But what about the troubling rise of entropy? Wouldn't each cycle grow more disordered, eventually leading to a cosmic heat death? Roger Penrose's conformal cyclic cosmology offers a breathtaking solution. He proposes that in the far, far future, when the universe has expanded into an utterly dark, cold, and empty void, the only remaining entities will be massless particles like photons. At this point, the concept of scale becomes meaningless. An infinite, empty universe becomes mathematically identical to a hot, dense Big Bang. The end of one eon seamlessly becomes the beginning of the next, with all the accumulated entropy effectively erased because there is no matter left to carry it. In this conformal rescue, the universe forgets its size and its disorder, allowing for a fresh, low-entropy start. Penrose even suggests we might find fossils of these previous eons imprinted on our own sky. He claims to have found evidence in the cosmic microwave background, in the form of concentric circles of slightly raised temperature. These circles, he argues, could be the ghostly imprints of supermassive black holes from a previous eon, their colossal collisions sending gravitational shockwaves that left a permanent mark on the subsequent universe's birth. These features, dubbed Hawking points, remain highly controversial, with many scientists arguing they are simply statistical anomalies within the cosmic background noise. If cyclic models are correct, what role do black holes play? They could be the universe's ultimate recycling centers. Some theories suggest that the information swallowed by black holes in one cycle is not lost forever, but is somehow encoded into the fabric of the next universe, perhaps seeding the formation of new structure. This transforms black holes from tombs into wombs, crucial agents in the eternal return. Could this endless cycle eliminate the need for an absolute beginning, making creation an eternal process without a creator? The idea is philosophically staggering, suggesting that existence itself is a fundamental, unending fact. We are left to wonder if we are living in just one of an infinite number of iterations, where the same fundamental patterns of galaxies, stars, and perhaps even life play out again and again in a cosmos that forever remembers how to begin. The most destructive objects in the cosmos might also be its most creative. Visualize a black hole not as a final tomb, but as a cosmic womb, a potential gateway to an entirely new reality. This radical shift in perspective comes from theories like black hole cosmology, which speculate that the immense gravitational collapse at the heart of a black hole could trigger the birth of a new universe, separate and entire. Within the unfathomable singularity, where our known laws of physics break down, the fabric of space-time might be twisted and reborn, creating a new cosmic bubble in an infinite multiverse. Physicist Lee Smolin takes this idea even further with his theory of cosmic natural selection. He proposes that universes can actually evolve. In this scenario, a universe that produces more black holes has a greater number of offspring, new universes with slightly tweaked physical constants. Over cosmic time, universes fine-tuned for black hole production would come to dominate the multiverse, just as natural selection favors organisms fine-tuned for reproduction. This provides a stunning, non-theological explanation for why our own universe seems so perfectly set up for making black holes, from the life cycles of massive stars to the mergers of galaxies. At the heart of this creative process lies the infamous black hole information paradox. Quantum mechanics insists that information, the distinct identity of every particle that falls in, can never be truly destroyed. But general relativity, with its ruthless event horizon and central singularity, suggests that all that information is irretrievably lost. This contradiction has forced physicists to reconsider the nature of the event horizon itself. One proposed solution is the firewall paradox, the unsettling idea that the event horizon might not be a smooth gateway but a searing wall of high-energy particles that would incinerate anything crossing it. This violent solution attempts to preserve information by destroying the infalling object before it can contradict quantum law, but it creates new problems, violating the principle of equivalence that is a cornerstone of Einstein's theory. A more elegant and profound resolution comes from the holographic principle. It suggests that all the information describing the three-dimensional volume of a black hole is not lost inside, but is perfectly encoded or painted onto its two-dimensional event horizon. The surface of the black hole acts like a cosmic hard drive, storing the complete data of everything that ever fell in. This leads to an incredible possibility. If our own universe is expanding and cooling from an initial singularity, could that singularity be the interior of a black hole in a larger parent universe? In this mind-bending picture, every black hole that forms in our cosmos could contain within it the seed of a new, expanding universe, forever hidden from our view. The matter that falls in provides the raw material, and the encoded information on the event horizon provides the blueprint. If black holes are not endpoints but creative engines, birthing new realities with slightly different physical laws, then the very meaning of existence is transformed. We are no longer just inhabitants of a single cosmos, but potentially part of an infinite, branching tree of universes, each born from the gravitational death of a star in a reality above. This redefinition of cosmic purpose inevitably draws our attention back to our own universe, prompting us to take a final, comprehensive inventory of everything it contains, and to confront the startling fact that most of it is still missing from our view. Our universe is overwhelmingly made of matter, a simple fact with a deeply puzzling origin. Every particle of dust, every star, and every galaxy is composed of it. Yet we know with certainty that the Big Bang should have created a perfect, balanced mirror of matter and antimatter. For every proton, there should have been an antiproton. For every electron, a positron. Had this perfect symmetry held, every particle would have met its opposite, annihilating in a final flash of light, leaving behind a cosmos of pure radiation. The fact that we exist at all means this symmetry was profoundly broken. Something in the early universe tipped the scales, leaving behind a tiny surplus of matter, just one extra particle for every billion annihilations. That one in a billion remnant is everything we see. This is the Baryon asymmetry problem, and it is one of creation's most fundamental mysteries. The Russian physicist Andrei Sakharov laid out the three essential conditions needed to generate this imbalance. The universe had to be out of thermal equilibrium, meaning it was not in a uniform, stable state. It needed processes that violated CP symmetry, the combined symmetry of charge and parity. And it needed interactions that violated Baryon number, meaning the total amount of matter could change, while the hot, expanding early universe naturally provided the first condition. The search for the other two has defined decades of particle physics. We have found CP violation. In experiments at places like CERN, we observe that certain subatomic particles, like neutral kaons and B mesons, decay slightly differently than their antimatter counterparts. It is a tiny, subtle effect, a 1% preference in a specific process, but it proves the laws of physics are not perfectly symmetrical between matter and antimatter. The universe has a built-in bias. The challenge is that the amount of CP violation we have measured in the lab is far too small to account for the vast amount of matter we see in the cosmos. It is like finding a single drop of water when we need to fill an ocean. This discrepancy points to physics beyond our current standard model. One compelling idea is leptogenesis. This theory suggests the initial asymmetry did not begin in the matter we see, but in the ghostly realm of neutrinos. Extremely heavy, right-handed neutrinos in the early universe could have decayed in a CP-violating way, producing a slight excess of ordinary matter over antimatter. This lepton asymmetry was then converted into a Baryon asymmetry through a spectacularly named process involving sphalerons. A sphaleron is a hypothetical, high-energy transition that can change a lepton, like a neutrino, into a baryon, like a quark. These processes, active in the searing heat of the early cosmos, could have reshuffled the initial neutrino imbalance into the proton and neutron surplus we live with today. To test these ideas, we look for echoes of that primordial conflict. The alpha magnetic spectrometer, a sophisticated particle detector mounted on the International Space Station, tirelessly sifts through cosmic rays. One of its primary goals is to find the unmistakable signature of anti-helium nuclei. Finding even a single one of these complex antimatter atoms would be revolutionary, as it could indicate the existence of pockets of primordial antimatter, surviving relics from the universe's first moments that never found their matter counterparts to annihilate with. So far, none have been found, deepening the mystery. Does this profound cosmic asymmetry, this preference for existence over annihilation, hint at undiscovered particles or entirely new forces that operated only in the universe's first fleeting instants? Solving this puzzle is not just about accounting for the stuff we are made of. It is about understanding why creation favored structure over emptiness, form over void. This fundamental imbalance, written into the laws of physics, may be the very reason anything complex, including us, could ever emerge. That single, giant cold spot on the cosmic map is far more than a statistical blip. It is a vast, mysterious region in the constellation Eridanus, a chill in the universe's background radiation so large and so profound that it defies easy explanation. Known simply as the cold spot, this anomaly stretches over 1 billion light-years across, a cosmic bruise that should not exist according to our standard models of inflation. When scientists first confirmed its existence in the Wilkinson microwave anisotropy probe data, and later with the higher-resolution Planck satellite, it sent a ripple of excitement and unease through the cosmology community. The simplest explanation seemed to be a colossal void, an immense region of space nearly empty of galaxies and dark matter. If such a void existed, light traveling through it would lose energy climbing out of its shallow gravitational well, a phenomenon known as the integrated Sachs-Wolf effect, which would manifest as a cold patch in the cosmic microwave background. Astronomers did indeed find a candidate, the Eridanus supervoid, but there is a problem. The void is not nearly large enough or empty enough to account for the profound cold we observe. The scale is wrong, leaving the cold spot as a stubborn, unexplained ghost in the machine. Could it be the imprint of a cosmic texture, a hypothetical defect in spacetime left over from a phase transition in the early universe, a kind of cosmic knot that unraveled and left a scar? Or, as theorist Laura Mersini-Houghton suggests, could it be something even more profound, the bruise from a collision with another universe in the vast multiverse? The cold spot is not the only large-scale anomaly that troubles our view of a perfectly uniform cosmos. Look at the entire map of the cosmic microwave background, and you will see a distinct lopsidedness, a hemispherical power asymmetry. One half of the sky shows stronger temperature fluctuations than the other, as if the universe's initial expansion was slightly more vigorous in one direction. This is coupled with the CMB dipole, a much larger temperature difference that we have long attributed to our own motion through space. We are moving towards the constellation Centaurus, and this motion should create a hot spot in front of us and a cold spot behind, like running through a gentle rain and feeling it more strongly on your face. Yet, some studies suggest this dipole is slightly too strong, that our local motion may not fully account for the entire signal. Could part of this asymmetry be primordial, a fundamental dipolar quality woven into the fabric of the universe at its birth? The statistical significance of these features, carefully measured in the Planck data, is too high to be comfortably dismissed. The probability that they are all random flukes is less than 1%, forcing cosmologists to confront the unsettling possibility that the cosmological principle, the bedrock idea that the universe is homogeneous and isotropic, might be only approximately true. Are we seeing the limits of our cosmic horizon, hints of a larger, more complex topology beyond what we can observe? Or do these irregularities point to a pre-inflationary era, a time before the rapid expansion when the universe was a chaotic, seething place whose initial wrinkles were never completely ironed out? These are not just minor curiosities, they are potential cracks in the foundation of modern cosmology, suggesting that our universe may have a preferred direction and a memory of its tumultuous origins. If these anomalies are real, they do not just challenge our models, they invite us to imagine a cosmos far more textured and strange than we ever believed. The shape of our universe might be far more intricate than an infinite flat sheet. What if space in its entirety is folded back on itself in a complex, finite form? This is the domain of cosmic topology, the study of the universe's global geometry and connectedness. Think of the surface of a balloon. It has a finite area, yet you can travel across it forever without ever finding an edge. Our three-dimensional universe could be analogous, a finite volume without any boundaries. Its overall shape is determined by its curvature, a concept arising from Einstein's general relativity. We measure this curvature through the patterns in the cosmic microwave background. The prevailing evidence strongly suggests our universe is flat, like an endless sheet of paper. But this flatness does not necessarily mean infinite. A piece of paper can be rolled into a cylinder, a finite but unbounded surface. In 3 dimensions, the simplest such shape is a 3-torus, like a giant donut. If you sailed a spaceship in one direction in a toroidal universe, you would eventually return to your starting point from the opposite direction, having never encountered a wall. This has a startling implication. If the universe is small enough, the light from a single, brilliant galaxy could have taken multiple paths to reach us. We might see the same cluster of galaxies repeated in different parts of the sky, like a hall of mirrors on a cosmic scale. Scientists like Jean-Pierre Luminet have explored even more complex shapes, such as the Poincaré dodecahedral space. In this model, the universe is a 12-sided cell whose opposite faces are connected. light wraps around this cell, creating a specific pattern of correlated circles in the cosmic microwave background. Teams have scoured the CMB data for these telltale pairs of matching circles, a ghostly signature of a universe that wraps around itself. So far, no definitive evidence has been found, but the search continues. The very presence of dark energy plays a crucial role in this geometry. A universe with positive curvature, like a giant sphere, would eventually collapse under its own gravity. A universe with negative curvature, like a saddle, would expand forever but in a diluted, disconnected way. Our flat universe, driven by dark energy, is poised for perpetual, accelerated expansion, a geometry that allows for the complex topology we search for. Could the large-scale anomalies in the CMB, like the cold spot and the axis of evil, be hints of this wrapping, a glimpse of the universe's true, finite shape? If spaces multiply connected, it would mean that every point is ultimately linked to every other, a profound cosmic unity written into the fabric of reality. This interconnected geometry forces us to ask if the universe's fundamental shape is a frozen relic from its first moments, a permanent imprint of creation. That initial architecture could not have formed without the precise calibration of the cosmic forces that carved it. The universe began in a state of perfect unity, a single primordial force. In that first searing moment, all of nature's interactions were one, bound together by a symmetry so profound it is difficult to fathom. Then, as the cosmos expanded and cooled, it underwent a series of cosmic phase changes, each one breaking the original symmetry and giving birth to the four distinct forces we recognize today. This grand unification is the hidden engine behind every cosmic pattern we see. Gravity was the first to peel away, shaping the large-scale architecture of the cosmos. Then the strong nuclear force separated, binding quarks into protons and neutrons and holding atomic nuclei together. Finally, the electroweak force split into the electromagnetic force, which governs light and chemistry, and the weak nuclear force, responsible for radioactive decay. This step-by-step unlocking of the forces created the rulebook for our reality, the work of physicists like Abdus Salam, who helped unify the electromagnetic and weak forces into the electroweak theory, showed that two seemingly different forces are actually manifestations of a single, deeper interaction at high energies. This triumph of unification hints at an even grander goal, a theory of everything that would weave gravity into the same tapestry. String theory is one such ambitious attempt, proposing that the fundamental constituents of reality are not point-like particles but tiny, vibrating strings. The different vibrational modes of these strings would correspond to different particles and forces, suggesting that all of creation is, at its heart, a form of cosmic music. This search for unity is not just philosophical, it has tangible consequences for the structure of the universe. The relative strengths of these forces were set during those early symmetry breaks, and they are exquisitely fine-tuned. If the strong nuclear force were just a few % weaker, atomic nuclei would not form and stars would never ignite. If gravity were significantly stronger, the universe would have collapsed long before life could arise. These forces act as cosmic sculptors. Electromagnetism, for instance, does more than just create light. It plays a crucial role in the formation of cosmic magnetic fields. These vast, invisible fields stretch between galaxies, influencing how gas collapses to form stars and guiding the swirling motions of galactic disks. To probe the highest energies where these forces might reunite, physicists propose ideas like supersymmetry. This elegant theory suggests every known particle has a superpartner, a heavier, unseen twin. If correct, it would solve major puzzles in particle physics and provide a candidate for the dark matter that holds galaxies together. The very model of cosmic inflation which set up the initial conditions for the universe relies on a scalar field, a kind of energy field that drove the rapid expansion, and its decay is thought to be connected to the same symmetry breaking that gave us the distinct forces. The recent detection of gravitational waves from colliding black holes and neutron stars offers a new way to test these ideas. These ripples in spacetime are a direct probe of gravity in its most extreme regime, and they could carry echoes of the universe's unified infancy. Could a final theory of everything reveal a single, beautiful equation from which all cosmic patterns, from the spin of a galaxy to the bonds of an atom, inevitably flow? This quest suggests that the universe's breathtaking complexity emerges from a foundation of stunning simplicity. Two black holes spiral inward, locked in a final, frantic dance. As they collide and merge into a single, more massive object, they unleash a torrent of energy, shaking the very fabric of space and time. These vibrations are gravitational waves, and their first direct detection in 2015 by the LIGO Observatory opened an entirely new sense for exploring the cosmos. For decades, visionaries like Kip Thorne championed the idea that such colossal events would send ripples across the universe, a prediction born from Einstein's general relativity. Until LIGO, our view of the universe was based entirely on light, from radio waves to gamma rays. Now we can hear it. This new sense of hearing reveals cosmic patterns hidden from our eyes. The faint chirp of a gravitational wave signal tells a detailed story about its source, whether it is the merger of two black holes, the collision of two ultra-dense neutron stars, or the cataclysmic explosion of a supernova. Each event leaves a unique fingerprint in the waveform, allowing scientists to weigh the objects involved and test Einstein's theory in the most extreme gravitational environments imaginable. The event known as GW170817 was a landmark. It was the first time gravitational waves were detected from the merger of two neutron stars, and crucially, telescopes around the world and in space saw the same event as a brilliant gamma ray burst and a glowing kilonova. This multi-messenger observation confirmed a long-held theory that the violent collisions of neutron stars are cosmic forges, creating the universe's heaviest elements like gold, platinum, and uranium. The gold in a wedding ring or the uranium that powers reactors was likely born in such a spectacular collision billions of years ago, but the most tantalizing ripples are still out there, waiting to be heard. Scientists are searching for a faint, omnipresent hum known as the stochastic gravitational wave background. This would be the combined rumble from countless events throughout cosmic history, a chorus of whispers from the earliest times. Some models suggest this background could even contain a fossil imprint from the inflationary era, a time before the cosmic microwave background, when quantum fluctuations in gravity itself were stretched to cosmic proportions. To listen for this primordial symphony, we need even more sensitive ears. Future observatories like the space-based LISA mission will detect waves from supermassive black hole mergers, events too low frequency for ground-based detectors. By tuning into these deeper cosmic rhythms, we could potentially hear the birth cries of the universe, vibrations from a time when the fundamental forces were still one. Do these faint ripples carry encoded information about the multiverse, a vibration from a neighboring cosmos brushing against our own? Gravitational waves are more than just cosmic messages. They are the very echoes of creation, guiding us to listen ever more deeply to the universe's hidden score. Our universe, with its finely tuned constants and elegant patterns, might not be a singular masterpiece but one of countless variations in an infinite cosmic library. This is the Multiverse Hypothesis, a compelling idea that what we call reality is just one bubble in a frothing sea of endless creation. it emerges naturally from our most successful theories. Eternal inflation suggests that the rapid expansion of space never truly stopped everywhere, but instead continues eternally, spawning new pocket universes with every quantum flicker. Meanwhile, string theory presents a landscape of staggering possibility, with perhaps 10 to the 500 different stable vacuum states, each one a potential universe with its own unique set of physical laws. Physicist Max Tegmark has helpfully categorized this dizzying prospect into 4 levels. Level 1 is the simplest, an extension of our own infinite space, where beyond our cosmic horizon, every possible configuration of matter is repeated, meaning there are infinite copies of Earth and of you playing out every possible life. Level 2 consists of the inflationary bubbles, each with different fundamental constants, perhaps where gravity is stronger or the weak force is weaker, universes where stars never form or where chemistry is impossible. Level 3 is the quantum many-worlds interpretation, where every quantum decision branches reality into a new universe, creating an ever-splitting tree of possibilities. And Level 4, the most speculative, proposes that every mathematically consistent structure actually exists as a physical reality. The primary appeal of this vast ensemble is its elegant solution to the problem of fine-tuning. In a multiverse, we should not be surprised to find ourselves in one of the rare, habitable universes, just as a fish should not be surprised to find itself in water. Yet this very strength is also its greatest weakness, the lack of direct, testable evidence. How do you prove the existence of something forever beyond our causal reach? Scientists are not giving up. They search for potential signatures, like a bruise in the cosmic microwave background from a long-ago collision with another bubble universe, or strange statistical anomalies in the distribution of galaxies that hint at a larger topological structure. The debate even extends to entropy. Is our universe's incredibly low initial state a rare fluke, or is it typical for a universe that can produce observers? If the multiverse is real, what does it mean for the intricate patterns we have traced? Does it diminish their significance, rendering them mere local bylaws in an infinite cosmic federation? Or does it amplify the wonder that, against all odds, our particular slice of existence found a way to weave such breathtaking complexity from a random draw of the cosmic lottery? This line of thinking inevitably pulls consciousness to the forefront, forcing us to ask if a universe can even be said to exist without a mind to observe its patterns. A single electron can be in 2 places at once, but only until we look at it. This strange truth lies at the heart of quantum mechanics, where particles exist as a cloud of probabilities, a superposition of all possible states, until a measurement forces them to choose a single, definite reality. This is the observer effect, and it forces a profound question about our role in the cosmos. Does the universe require a conscious mind to bring it into being? The Copenhagen interpretation, formulated by pioneers like Niels Bohr and Werner Heisenberg, argues that yes, the act of observation is what collapses the wave function, transforming possibility into concrete fact. Without an observer, reality remains a blur of potential, a ghostly tapestry of what could be. This idea was spectacularly illustrated by the double-slit experiment. When particles like electrons are fired one by one at a barrier with 2 slits, they behave like waves if no one is watching, creating an interference pattern of multiple possibilities on the detector screen. But the moment a device is placed to observe which slit each electron passes through, the wave-like behavior vanishes. The electrons begin acting like discrete particles, and the interference pattern disappears. The very act of asking which path it took forces the electron to pick just one. This suggests that at the most fundamental level, the universe is participatory. Physicist John Archibald Wheeler took this concept to its ultimate conclusion with his participatory anthropic principle. He envisioned the universe as a self-excited circuit, a grand loop where consciousness is not a late-arriving accident but an essential feature. In this view, observers, meaning us and any other conscious beings, are necessary to bring the universe into existence, not just now, but in a backwards-reaching way through time. We are not just living in the universe, we are bringing it into being. But how does the definite world we experience emerge from this quantum fog? The process is called decoherence. It explains how a quantum system interacting with its environment, like a particle bouncing off air molecules or radiating heat, quickly loses its quantum properties and appears to behave classically. The environment acts as a continuous observer, constantly measuring the system and causing its wave function to collapse without the need for a human mind. This is why baseballs and planets have fixed positions, while isolated electrons do not. Yet, this only pushes the hard problem of consciousness one step back. Why should any physical process, whether a collision of atoms or the firing of neurons, give rise to subjective experience at all? Why is there an inner world accompanying the brain's biochemical machinery? If consciousness is fundamental, some speculate that the large-scale structures of the cosmos, the vast neural networks of the cosmic web, might be more than just a visual analogy. Could they be a physical manifestation of a universal mind, a cosmic consciousness of which we are a small, self-aware part? The same fractal patterns that appear in a fern frond and a river delta also appear in the distribution of galaxies. Is this self-similarity a hint that mind and cosmos are woven from the same fabric? Are we the universe's way of becoming aware of itself, or is our own awareness merely a beautiful, intricate, and ultimately accidental pattern that emerged from the blind churn of physics? The answer to this question may lie not in the nature of mind, but in the very geometry of the cosmos, in the subtle mathematical symmetries that dictate how everything fits together. The same branching pattern appears in a bolt of lightning, a leafless tree in winter, and the vast, empty voids between galaxies. This is the signature of fractal geometry, a hidden rule where patterns repeat themselves at different scales, a universe obsessed with its own design. A fractal shape looks equally complex whether you are observing it from a mile away or under a microscope. Its core principle is self-similarity. Coastlines, clouds, and mountain ranges all share this property, and so does the cosmos itself. The mathematician Benoit Mandelbrot first gave this recursive beauty a name and a mathematics, revealing a world built not on smooth lines, but on infinitely complex, rough-edged forms. When we map the universe on its grandest scale, this fractal nature becomes undeniable. Galaxy surveys, like the Sloan Digital Sky Survey, reveal that matter is not scattered randomly. Galaxies cluster into groups, which themselves cluster into larger superclusters, in a pattern that looks roughly the same whether you are mapping a region 100 million light-years across or a billion. This is scale invariance, the hallmark of a fractal. To quantify this, scientists use the concept of fractal dimension. A smooth line has a dimension of 1. A completely filled-in plane has a dimension of 2. The cosmic distribution of galaxies has a dimension between 1 and 2, meaning it is more than a simple line of structure but does not fully fill the volume of space. It is a sponge-like, complex network whose intricate branching traces out a specific mathematical value. This pattern emerges from the chaotic flow of the early universe. The same turbulence that shapes eddies in a river or the swirls in a cup of coffee played a role in the distribution of primordial gas. As vast clouds of hydrogen collapsed under gravity, turbulent motions created dense filaments and knots, a fractal cascade that determined where the first stars would ignite. This turbulence is a physical engine that naturally generates fractal patterns, channeling matter into the delicate, branching arms of spiral galaxies and the web-like filaments that connect galactic clusters. But how did this turbulent, fractal potential get written into the fabric of spacetime in the first place? The answer may lie in cosmic inflation. That initial burst of hyper-expansion is thought to have taken the quantum fluctuations of the newborn universe, which themselves have a fractal, self-similar character, and stretched them across the entire sky. Inflation acted as a cosmic projector, taking a microscopic fractal blueprint and magnifying it to a scale larger than the observable universe. The patterns we see in galaxy clusters today are therefore the grown-up versions of those initial quantum seeds, their fractal geometry preserved and amplified across billions of years. This recursive beauty forces a profound question upon us. Does the prevalence of fractals, from the branching of a river delta to the structure of the cosmic web, imply that the universe is running a single, universal algorithm for creation? Is there a fundamental computation, a set of simple recursive rules that, when iterated over and over, generates all the complexity we see? Or are these patterns simply the inevitable, beautiful outcome of blind physical laws like gravity and turbulence playing out on a canvas of unimaginable size? The haunting self-similarity between a neural network and the cosmic web suggests a deep resonance across scales, a hint that the same mathematical principles might govern the growth of a brain and the growth of a universe. This recursive architecture, this echo of pattern within pattern, ultimately draws our gaze back to the very beginning, to the mysterious singularity from which this infinite complexity first bloomed. Our laws of physics dissolve into pure speculation at the moment of the Big Bang. That initial singularity, a point of infinite density and temperature, represents the ultimate edge of our understanding, a place where general relativity and quantum mechanics both fail. Asking what came before seems like a logical impossibility, because time itself may have begun at that instant. Yet, our curiosity pushes us to peer beyond that veil, to explore theories that attempt to describe the indescribable. Stephen Hawking approached this enigma with his no-boundary proposal. He suggested that if we could rewind the cosmos to its very beginning, we would find that time behaves like a dimension of space. Imagine the North Pole on a globe. There is no point on Earth north of the North Pole, it is the boundary. In Hawking's model, the beginning of the universe is like that pole, a smooth, finite point without a sharp edge or a before. In this view, the question of what came before the Big Bang becomes meaningless, as time as we know it did not exist. This elegant idea redefines creation not as an explosion in a void, but as the spontaneous emergence of everything from a singular geometric condition. Another compelling idea is the quantum bounce. This theory replaces the singular beginning with a transformation. Picture our universe not as a one-time event, but as a single breath in an eternal cycle. In this scenario, a previous cosmos, perhaps similar to our own, contracted under its own gravity. Instead of collapsing into an infinitely dense point, quantum gravity effects would have become so powerful that they generated a repulsive force causing a great bounce. That bounce would then have become our Big Bang, launching the expansion we observe today. This model elegantly sidesteps the need for a definitive beginning, suggesting an endless rhythm of contraction and rebirth. String theory offers its own escape from the singularity. In the ekpyrotic model, our three-dimensional universe exists as a membrane or brain floating within a higher dimensional space. The Big Bang, in this view, was not a moment of creation from nothing, but the aftermath of a colossal collision, another parallel brain moving through the higher dimensional bulk could have slammed into our own. The immense energy of that impact would have heated our brain to an incredible temperature, flooding it with matter and radiation, and setting off the expansion we mistake for a beginning. This paints a picture where our entire cosmic history is just one chapter in a much larger, multidimensional story. So, could the universe have no true beginning? The combined weight of these theories, from the no-boundary condition to cyclic brain collisions, suggests that our cosmic home may not have been born from a singular, inexplicable event. It might instead be eternal, a timeless, self-sustaining reality where phases of expansion and contraction are as natural as the changing of seasons. This redefinition forces us to confront the very nature of existence. Is the concept of a beginning merely a limitation of our human perception, a story we tell to make sense of a reality that is infinitely more complex? The answer, if we can ever find it, lies hidden in the quantum gravity that governed the universe's first fleeting moment. That river of time feels so absolute, yet its source remains the ultimate cosmic enigma. We experience time as a relentless one-way flow, but modern physics dares to ask if this flow is just an illusion, a surface feature emerging from a deeper, timeless reality. In the quest to unify general relativity with quantum mechanics, time itself becomes a problem. The equations of loop quantum gravity, championed by physicists like Carlo Rovelli, suggest that time is not a fundamental ingredient of the universe. Instead, it might be a derived property, much like temperature emerges from the frantic motion of atoms. At the most fundamental level, the fabric of spacetime could be woven from discrete, quantized loops, and our familiar experience of time would simply be a consequence of how these loops interact and entangle on a large scale. This radical rethinking is crystallized in the Wheeler-DeWitt equation, a foundational equation of quantum cosmology that attempts to describe the entire universe as a quantum object. Astonishingly, this equation completely lacks a time variable. It paints a picture of a static, frozen universe, a single block of reality where past, present, and future simply are. This is the problem of time in its purest form. If the most basic description of our cosmos has no time, then where does our powerful, undeniable experience of its flow come from? Stephen Hawking offered a profound way to visualize this timeless beginning with his concept of imaginary time. In this mathematical approach, time behaves like a fourth dimension of space, especially near the Big Bang. Imagine the beginning of the universe not as a sharp point in time, but as a smooth, rounded region like the South Pole of a globe. There is no singularity, no edge, and no before. The question of what happened before the Big Bang becomes as meaningless as asking what is south of the South Pole. In this no-boundary proposal, the universe would be completely self-contained, without a beginning or an edge in imaginary time. Yet we are still left with the stubborn arrow of time, the reason we remember the past and not the future. This directionality is inextricably linked to the second law of thermodynamics and the increase of entropy. Our universe began in a state of incredibly low entropy, a highly ordered and improbable configuration. Everything that has happened since, from the formation of galaxies to the burning of stars, has been a long, slow slide into higher states of disorder. It is this cosmic progression from order to chaos that gives time its apparent direction. Our consciousness, our memories, and our very sense of a flowing present may all be artifacts of this universal journey toward higher entropy. So if time is not fundamental, but emerges from a timeless quantum state alongside space and matter, what does that imply for causality? The very idea that a cause must precede an effect seems to be built into our logic, but if time itself has a beginning, then the first cause stands outside of time altogether. This temporal mystery is not just a philosophical curiosity. It is the final frontier in our search for a theory of everything, a quest to understand how the timeless quantum bedrock of reality gives rise to the dynamic, evolving cosmos we call home. That single, elegant equation remains the ultimate prize, a formula that would weave together the cosmic and the quantum into one seamless tapestry. This is the dream of a theory of everything, a framework capable of describing every force and every particle, from the gravity that binds galaxies to the quantum jitters that fill the void. It is the final frontier in our quest to read the universe's deepest code. The greatest obstacle in this search is the chasm between our two most successful theories. Einstein's general relativity paints a beautiful picture of gravity as the curvature of spacetime, perfectly predicting the orbits of planets and the bending of light. Yet, in the frantic, probabilistic world of the quantum, where particles pop in and out of existence, this smooth geometric picture shatters. Unifying them is like trying to write a symphony for an orchestra that speaks two different, incompatible languages. Leading the charge are ambitious candidates like string theory. It proposes a radical idea that the fundamental building blocks of reality are not point-like particles, but unimaginably tiny, vibrating strings. The different vibrational modes of these strings, like the notes on a violin, would correspond to all the different particles we see. A string vibrating one way is an electron, another way is a quark, and another is a photon. In this view, the entire universe is a form of cosmic music. To make the mathematics of this symphony work, string theory requires more dimensions than the three of space and one of time we experience. We live our lives in a four-dimensional space-time, but the theory suggests there are 7 more spatial dimensions, curled up into shapes so small we can never perceive them directly. Physicist Edward Witten's work on M-theory, a unifying framework for different string theories, points to an 11-dimensional reality. These hidden dimensions are not science fiction, they are mathematical necessities, and their specific geometry could determine the values of nature's fundamental constants, like the strength of gravity or the mass of an electron. Another compelling path is loop quantum gravity. This approach takes Einstein's geometric view of spacetime seriously and quantizes it. Instead of a smooth continuum, space is proposed to be woven from a fabric of tiny, discrete loops. Picture the fabric of reality as a chainmail tunic, with each interlocking ring a tiny, indivisible unit of space. This network of loops, this spin foam, gives rise to the three-dimensional space we experience, and it naturally avoids the infinities of the classical Big Bang Singularity, suggesting a quantum bounce from a previous cosmos. Yet, for all their mathematical beauty, these theories face a monumental challenge: experimental verification. How do you test for strings or curled-up dimensions when they exist at energies 1 trillion times greater than our most powerful particle colliders can reach? This has led to the landscape problem in string theory. The mathematics suggests not one unique solution, but a staggering number of possible stable configurations, perhaps 10 to the 500. Each one represents a different universe with its own laws and constants. If true, our universe is just one tiny garden in an infinite cosmic landscape, and its particular features are not inevitable, but the result of a random selection. This brings us to a profound reflection. If we one day discovered a true theory of everything, would it reveal our universe as the only possible, logically necessary outcome? Or would it show us that our cosmos, with its specific patterns and constants, is merely one possibility in a vast multiverse of alternatives? The very pursuit of this final answer underscores a fundamental human drive, not just to understand the universe, but to truly know the mind behind its design, to see if its deepest logic mirrors our own. These intricate patterns invite a question that has haunted humanity for millennia. Is the universe merely a complex machine, or does it have a mind? For philosophers like Plato, the mathematical perfection of the cosmos was evidence of a deeper reality. He believed the physical world was but a shadow of perfect, eternal forms, ideal blueprints of which a circle or a spiral here on Earth is just a faint copy. This idea echoes through the ages, finding a voice in the teleological argument for a creator. The argument from design suggests that such intricate order, from the fine-tuned constants of physics to the spiral arms of a galaxy, points toward an intelligent designer, a cosmic architect who set the universe in motion according to a rational plan. Yet another perspective, pantheism, sees this order not as evidence of a separate creator, but as the inherent logic of a universe that is itself divine, a single, interconnected whole where nature and God are one and the same. This search for meaning is deeply woven into human culture. Our ancestors looked to the orderly procession of the stars and created myths and calendars, seeing the hand of gods in the turning of the seasons. Great cathedrals were built with proportions reflecting the golden ratio, an attempt to mirror cosmic harmony in stone and glass. In modern times, Carl Sagan championed the view that we are a way for the cosmos to know itself. He argued that the universe is fundamentally knowable through science, and that our ability to decipher its mathematical language is not an accident, but a profound connection. We use cosmic metaphors to understand our own lives, speaking of being torn apart by emotional black holes or experiencing a big bang of creativity. But what if the multiverse is real? This idea can feel profoundly disorienting. If our universe is just one bubble in an infinite froth of realities, then our specific patterns, our fine-tuning, our very existence might be reduced to a statistical fluke. The unique story of our cosmos becomes just one page in an infinite library, potentially stripping it of any special significance. Conversely, it could amplify the wonder that in this vast cosmic lottery, our particular ticket allowed for beauty, consciousness, and the ability to ask these very questions. So, do these grand cosmic designs give our individual lives purpose, or are we simply pattern-seeking creatures, projecting meaning onto a universe that is ultimately random and indifferent? The answer you lean toward may depend on whether you see the universe's logic as a message or simply as its native tongue. This contemplation of our place within the ordered whole naturally leads us to consider the responsibilities that come with such understanding. Our growing ability to read the cosmos comes with a profound responsibility. As we stand on the threshold of becoming an interstellar species, we must ask not only what we can do, but what we ought to do. The ethical questions we face are as vast as space itself. For instance, when we send a rover to Mars or a probe to the icy moons of Jupiter, we carry with us a cargo of earthly microbes. A single, resilient bacterium hitchhiking on our spacecraft could potentially contaminate a pristine alien environment, forever spoiling our chance to discover a second, independent genesis of life. This is why planetary protection protocols are so critical. Scientists like Jacob Hack-Misra argue for rigorous sterilization of our vessels, treating every new world as a potential sanctuary, a place we must approach not as conquerors but as careful guests. This principle of non-contamination is our first and most fundamental duty to the cosmos. But what if we are not the only guests at the table? The Fermi paradox, the puzzling silence of the cosmos despite the high probability of life, might have an ethical answer. Where is everybody? Perhaps advanced civilizations choose to remain quiet, practicing a form of cosmic restraint to avoid interfering with the fragile development of others. They might be listening like we are, but broadcasting only with great caution, if at all. This idea, sometimes called the zoo hypothesis, suggests that the great silence is not an emptiness but a sign of respect. It forces us to consider the potential impact of our own transmissions. Should we be actively broadcasting our presence into the galaxy, or is that an irresponsible act that could attract unknown dangers or disrupt a delicate galactic ecosystem? Our ethical considerations must also turn back toward our own world. Seeing Earth as a pale blue dot, a fragile oasis in the void, transforms our relationship with it. Stewardship of our planet is no longer just an environmental policy, it is a cosmic imperative. This is the only world we know for certain supports life, and its health is the foundation from which all our explorations must launch. The principles of the Outer Space Treaty, established in the 1960s, echo this sentiment, declaring that space is the province of all humanity, to be used for peaceful purposes and for the benefit of all countries. As we look to the future of space colonization, these moral questions become even more acute. If we establish a settlement on Mars, do we have the right to radically alter its environment through terraforming, effectively erasing its natural, if sterile, history? Or do we have an obligation to preserve other worlds in their pristine state as monuments to cosmic evolution? The resources of the solar system, from the minerals of asteroids to the water of icy moons, represent immense potential, but their extraction must be guided by principles of equity and sustainability, lest we simply project our old conflicts onto a new frontier. As we unravel the universe's grand patterns, we are also deciphering a code of conduct. How do we act to preserve the integrity of this magnificent creation we are only beginning to understand? The answers we forge will define not just our survival, but our cosmic legacy. A new generation of eyes is turning toward the sky, instruments of such power they will read the faintest ink in the universe's diary. These are not just upgrades, they are revolutions designed to probe the cosmic patterns we have just begun to trace and to find the ones we have not yet dreamed of. The James Webb Space Telescope is our newest time machine, its infrared gaze piercing the dust of nebulae to witness the birth of the very first stars and galaxies. It sees in a light our eyes cannot, studying the atmospheres of distant exoplanets, searching for the chemical fingerprints of water, methane, and even potential biosignatures, the gases that might be waste products or fuel for alien life. Astronomers like Natalie Batalha are using its data to transform exoplanets from distant points of light into worlds with weather, climate, and perhaps one day, a sign that we are not alone. But this is only the beginning. On a mountaintop in Chile, the Vera Sea, Rubin Observatory will soon embark on an unprecedented decade-long movie of the sky. Its giant camera will capture the entire visible sky every few nights, creating a time-lapse of the cosmos. It will map the positions and motions of billions of galaxies, revealing the dark matter scaffolding of the cosmic web in greater detail than ever before, and it will catch countless transient events, the sudden flares and explosions that punctuate the cosmic silence. Meanwhile, in the quiet of space, a different kind of observatory is taking shape. The Laser Interferometer Space Antenna, or LISA, will listen for the lowest frequency gravitational waves, the ripples from the mergers of supermassive black holes at the hearts of galaxies. This will open a new window onto the dark, violent universe, allowing us to hear the birth cries of these monsters and trace the history of galaxy formation through their collisions. And then there is the search for life itself. Mars sample return missions represent one of the most ambitious endeavors in the history of exploration. Rovers are now carefully collecting and caching tubes of Martian soil and rock. The plan is for a future spacecraft to retrieve these samples and bring them back to Earth, where our most sophisticated labs can scour them for fossilized or chemical evidence of ancient Martian life, a biosignature from our planetary neighbor. To peer even further back in time, to the very first moments, a new fleet of experiments is targeting the cosmic microwave background. CMB Stage 4 projects will create exquisitely detailed maps of this ancient light, searching for the faint imprint of primordial gravitational waves from the inflationary epoch. Finding that signature would be like hearing the echo of the Big Bang itself, providing the most direct evidence yet for the theory that our entire cosmic structure was born from a quantum tremor. And what of other minds? The search for technosignatures is evolving. Advanced radio arrays like the Allen Telescope Array are not just listening for stray signals, they are systematically scanning stars for patterns of unnatural origin, for structured communication that nature could not produce. What profound surprise awaits us in the next decade of observation? Will we find a planet with an atmosphere rich with oxygen and chlorophyll, a world painted green from orbit? Will we decode the gravitational wave hum from the dawn of time, or intercept a signal that is unmistakably engineered? Each new instrument is a key designed to unlock a deeper chamber in the cosmic mansion, bringing us closer to a final, unified understanding of the grand design. We have gathered the scattered pieces of this cosmic puzzle, and a startling portrait of creation is taking shape. The universe reveals itself not as a chaotic accident, but as a dynamic, evolving system governed by a deep mathematical logic. From the quantum jitters that seeded the first galaxies to the vast, spinning arms that define them, a single thread of order connects the infinitesimal to the immense. This is not a static masterpiece hanging in a museum. It is a living, breathing entity, still unfolding according to rules we are only beginning to decipher. The relentless push of dark energy and the puzzling alignments across billions of light years are not errors in the design. They are clues that our physics is unfinished, pointing toward a grander theory waiting to be found. Within this framework, cycles of birth and rebirth or a frothing multiverse become plausible narratives for an eternal creative process. Our very existence speaks to a crucial mechanism in this cosmic engine, symmetry breaking. The universe began in a state of perfect, featureless unity, but it was the breaking of this symmetry that gave us a world of rich diversity, from the dominance of matter over antimatter to the specific spin of a galaxy. This foundational bias is why anything complex exists at all, and why are we here to see it? The Anthropic Principle offers a stark yet profound answer. We observe this particular universe with its finely tuned constants because it is one of the rare, perhaps infinitely rare, bubbles in the cosmic landscape capable of hosting conscious life. The consistency of patterns across every scale, from the branching of a neuron to the filament of a supercluster, hints at a unified origin, a single set of instructions from which all complexity blossoms. So, do these revelations bring us closer to understanding the mind of the universe? In a way, they do, but not by giving us a simple answer. They reveal a cosmos whose fundamental nature is logic, structure, and a relentless drive toward complexity. The mystery deepens not into confusion, but into a more profound awe, as we stand before a creation that seems to be both a magnificent machine and a work of art, whose final secret may be that it is both at once. The universe's grandest designs are written in a language of mathematics and light. We have traced these patterns from the quantum tremor that sparked the cosmos to the vast, invisible webs of dark matter that give it structure. We have witnessed how a fundamental preference for matter over antimatter made our very existence possible, and how dark energy now guides the ultimate fate of everything. These are not isolated curiosities, but interconnected clues pointing toward a single, stunning reality. The cosmic blueprint is real, a set of instructions woven into the fabric of space-time that dictates how complexity emerges from simplicity. This knowledge transforms our place in the cosmos. We are no longer just inhabitants of a random rock, but conscious participants in an immense, evolving system. We are the universe becoming aware of itself, gifted with the ability to look back and decipher the code of our own creation. This perspective invites a profound humility, a recognition of how small we are in the vastness of space and time, yet how significant our capacity for understanding truly is. It fuels a sense of wonder that bridges the gap between the scientific and the spiritual, asking us not to choose between them, but to see the pursuit of knowledge as a form of reverence. The journey does not end here. Every answered question unveils a deeper layer of mystery, a more intricate puzzle waiting to be solved. We would love to hear which cosmic pattern captured your imagination the most. Was it the spooky alignments of the axis of evil, the fractal beauty of the cosmic web, or the fine-tuned constants that allow for life? Share your thoughts in the comments below. If you want to continue exploring the deepest mysteries of space with us, please subscribe. Remember, each time we decode a cosmic whisper, we are reading a page from the mind